In this video, we move on to the next step in our first unit, which is all about linear inequalities in two variables. Solving for linear inequalities in two variables is similar to how we graphed linear equalities in two variables, only we take it one step further from there. Let's look at a few examples. In the first example, we're graphing x minus y is less than or equal to 3. To begin with, what I recommend is replacing the inequality with an equality and graphing the line that way, just as we did in the last unit. So to graph any line, we generate 2 points, usually the x-intercept by letting y equal 0 and the y-intercept by letting x equal 0. So let's find those 2 points. Again, for the x-intercept, we let y equal 0, which leaves us with the equation x minus 0 equals 3, or in other words, x equals 3. So we have an x-intercept at 3, right here. To solve for our y-intercept, generating a second point, we let x equal 0. So we've got 0 minus y equals 3, or moving things over the equality or multiplying both sides by -1, we get y equals minus 3 for our y-intercept down here, which means this line, x minus y equals 3, looks like this. From here, we go back to the inequality, and here's where we take into account the inequality sign. What this means is that only one side of this line contains all the points that we want. Just like when we went from linear equalities in one variable and had an answer like x equals 5 to linear inequalities in one variable and had an answer like x is less than 5 that represented a whole region, we've got a similar thing happening here. With x minus y equals 3, we've got just this line as the answer. With x minus y less than or equal to 3, we've got either the entire region above the line as the answer or the entire region below the line as the answer. How do we figure out which region we want? We use a test point. I usually test the point 0, 0. So you take your test point, you plug it back in to see whether it ends up true or false. When we plug in x is 0, y is 0, we get 0 minus 0, which is 0, is less than or equal to 3. This is true, which means that 0, 0 is true, and every point that's on the same side as 0, 0 will all end up true, and every point that's not on the same side will end up false. So this side is false, and we call this side the feasible set. Any point in that region above the line would end up true when we plugged it into the inequality. Let's do one more example. 2x plus y is greater than 0. So again, we start out by setting this as an equality, generating our x-intercept. We let y equal 0 and solve, so we get 2x plus 0 equals 0, or in other words, x equals 0. But what we should notice here is that if we try to get the y-intercept by setting x equals 0, we're also going to get the same point, y equals 0. So we need to generate a different point now to connect the dots. So let's pick, let's pick x equals minus 1 and generate the y point. So if we set x equal minus 1, we end up with 2 times minus 1 is minus 2 plus y equals 0. Moving the minus 2 over, we get y equals 2. So this is the point where x is minus 1 and y is 2. So over here, x is minus 1, y is 2. There's our second point. And we can connect the dots. But wait before you draw this line. In the last example, we drew a solid line. But in this example, because our inequality is strictly greater than, not greater than or equal to, what it means is that the points on the line will actually end up false. They'll go with the false region. So we use a dashed line to represent these strict inequalities. And then we need to, again, pick a test point. We don't want to pick 0, 0 anymore because it's on our line now. So let's pick the point 1, 1 as a test point. We take 1, 1, we plug it in. We'll get 2 times 1 is 2, plus y is 1 is greater than 0. So this says 3 is greater than 0. But 3 is greater than 0. So this is true also. 3 is greater than 0. So our test point is true. Everything on the same point as the test point makes up our feasible set. And everything on the other side is false. In order to take this one step further, what we sometimes do is combine multiple inequalities on one graph, just like we could combine multiple equalities, lines, on one graph. So let's take our 2 examples that we just did and put them together. So we've got x minus y is less than or equal to 3, which, let's do this one in blue. Let's call it inequality 1. We had an y-intercept at minus 3. We had an x-intercept at 3. It was a solid line. And we wanted to keep everything above the line and get rid of everything below the line. For inequality 2, let's do this one in red. We had an x and y-intercept at 0, 0. We had a second point at minus 1, 2. We wanted to use a dashed line to represent this strict inequality. And we wanted to keep everything above the line again and get rid of everything below the line. So when we combine these 2 inequalities, what we end up with is a feasible set that's a little bit smaller. Just this triangle region up here ends up being our feasible set. And what's also really important when we combine multiple inequalities is that we can solve for the point of intersection and find the corner of that feasible set. So let's do that. If we look at our 2 inequalities, let's imagine them both as equalities. And let's solve for the point of intersection as we learned how to do in the last video. Let's use the substitution method. So we'll solve for one variable in one of the equations. Then we'll take that and sub it into the x place in the second equation. So we're putting in our x value from one equation to the other. Now we've eliminated all but one variable. Let's multiply through the brackets. 6 plus 2y plus another y equals 0. So in other words, 6 plus 3y equals 0. Moving the 6 over, 3y is minus 6. Dividing both sides by 3, we get y is minus 6 over 3, which is negative 2. We have our y coordinate. Now we can plug it back in to find our x coordinate. So x was supposed to be 3 plus y. We know y is minus 2. So 3 minus 2 leaves us with x equals 1. So our point of intersection is x is 1, y is minus 2. If we go back to our last slide, we can label the point as x equals 1. Oh, let's do it over here. X equals 1, y equals minus 2. That's it for solving linear inequalities in 2 variables. If you can do equalities, you can do inequalities. And in the next video, we'll take it one step further to add a word problem to there. See you then.